We've been working with the fundamental theorem of calculus and doing some problems with definite integrals. We just started that at the end of last class. Let's continue with that and do some more examples and find some area between the curve and the x-axis, and then we'll look at areas bounded between two different curves. That could be that will probably be a different video though, the two different curves. But the fundamental theorem of calculus says that if f is a continuous function on some interval a, b, and let capital F be any antiderivative of little f, then we can say that the integral that's bounded between a and b of f of x dx, that is equal to the antiderivative of f of x evaluated at the upper bound minus the antiderivative evaluated at the lower bound of that interval. And so looking at this next example, I have the integral from 1 to 8, and then in the numerator, I have 3 minus y raised to the 1/3 power, and then that's all over y raised to the 2/3 power, and then dy. So first thing we need to do is we need to find that antiderivative of the integrand, which is that quotient. And we could either try to do some use substitution, or we can try to manipulate it. But right now, how it's written, we don't know how to take that antiderivative. So I notice that's just one term in the denominator. And so I would probably rewrite this by splitting this up into two separate fractions and getting that variable then into the numerator by changing the sign of the exponent. So let's first do that. So maybe we can do some of this work on the side. If I have 3 minus y to the 1/3, and this is all divided by y to the 2/3, I could divide each piece by that y to the 2/3. And if I do that, then I can bring up the y to the 2/3 in the first fraction, rewriting it as 3y to the negative 2/3 minus. And so I have the same base division. I subtract my exponent. So my exponent on top minus my exponent on the bottom if I'm bringing it up. So 1/3 minus 2/3 gives me a negative 1/3. So now we've rewritten that integrand so that we can go ahead and just integrate without any substitution. So the integral from 1 to 8 of 3y to the negative 2/3 power minus y to the negative 1/3 power, all this dy. Okay, so now we're ready to take the antiderivative. And so remember, so this is just a variable raised to a power. So we're just going to add 1 to our exponent and divide by that new exponent. And that gives us the antiderivative. So we have 3y adding 1 to negative 2/3. So 3/3 minus 2/3, that's going to give me a 1/3 power. If I'm dividing by a fraction though, remember it's the same thing as multiplying by the reciprocal. So dividing by 1/3 is the same thing as multiplying by 3. And then we have this minus. Okay, so again, we're going to add 1 to our exponent. So negative 1/3 plus 1, which is 3/3. Negative 1/3 plus 3/3 is a 2/3. Divide by that exponent of 2/3 is the same thing as multiplying by the reciprocal, which is 3/2. And because this is not an indefinite integral, indefinite integrals didn't have the bounds, it was just that integral sign with no number on top and the bottom. We write this vertical line to say that we're going to go in here and we're going to go back and we're going to reevaluate this, where our top bound is 8 and our lower bound is 1. So we're technically looking at f of 8 minus f of 1. Okay, so I noticed that I can clean this up a little bit. To me, if I have a exponent that is rational, I normally like to rewrite that if I'm evaluating things that with numbers, I like to rewrite that with a radical. And so I'm going to rewrite this is the same thing as 9 cubed root of y minus 3/2. So the denominator is what root we're taking. So the cubed root, oops, and that can go in the denominator, right? Because that has a negative exponent. So let me make that positive, bring it down. Actually, I'm sorry. I'm looking above 2/3. It stays up there. That was right first. Okay, so rewriting y to the 2/3, that's a cubed root of y. And then I can either square it underneath the radical or I can square it after I take the cubed root. Well, if that root comes right out, it's easier to do the exponent, that power, after you take the root. So you're not dealing with such big numbers. And again, we're evaluating this from 8 to 1, 1 to 8. So we're going to go in here and we're going to plug in our 8 value wherever we see a y. And so we have 9 cubed root of 8 minus 3/2 cubed root of 8 quantity squared. And then we subtract off f of 1, but it's more than one term for our antiderivative. So we need to make sure we put parentheses or brackets around this whole expression once we plug 1 in. And so plugging in 1, we have 9 cubed root of 1 minus 3/2 cubed root of 1, and then that's squared. Okay, so we think to ourselves, what am I cubing to get back 8, which is 2? So we have 9 times 2 minus 3/2. Again, what will we cube to get 8, which is 2? But then I have that 2 is squared. So that will give me 4 here, times 4. Minus, bracket. So 9 times the cubed root of 1. Cubed root of 1 is 1. So 9 times 1 is 9. Minus 3/2. And cubed root of 1 is 1. And 1 squared is 1. So it's just that minus 3/2 there. So we have 18 minus, I notice I can clean this up a little bit, get rid of my denominator. 2 goes into 4 twice. So minus 3 times 2, which is 6. Minus, let's distribute this negative. So minus 9, and then a plus 3/2. Okay, so combining that all together, 18 minus 6 is 12. 12 minus 9 is 3. So I have 3 plus 3/2. Let me rewrite 3/2 while I bring that down. 3/2 is the same thing as 1 and 1/2. So 3 plus 1, that's 4. So this is 4 and 1/2. So we just found that definite integral bounded between 1 and 8. So here's another example that we're going to apply the fundamental theorem of calculus to help us find this definite integral. And we have the integral from 1 to 2 of the quotient, which is 3 in the numerator, all divided by x times that quantity 1 plus natural log of x. And that's all in the denominator, and then times dx. So looking at this, it's not just one term in that denominator. So I can't break it up as separate fractions. I can't bring things up into the numerator. That's not going to help me any. Also, I don't know if you remember us, did we ever talk about taking the integral or antiderivative of natural log of x? Can you think of something that would give us the derivative? If we took the derivative, it would give us the natural log of x. And the answer to that question is no. So if there's something in there you don't know how to integrate, then sometimes that's what you should choose u to be. So let's try choosing u to be that whole parentheses. And so if we choose u to equal 1 plus the natural log of x, we then went through with this substitution method. We took the derivative of both sides of what we chose u to be. So the derivative of u is 1 with respect to u, so du equals the derivative of 1 is 0, plus the derivative of the natural log of x. The derivative of natural log of x is 1 over x dx. So we needed to go back into our integral and this dx and replace it in terms of u. So we weren't done once we took the derivative of both sides. Once we chose our u, we had to solve for dx. And so to solve for dx here, we're going to just multiply both sides by x. So multiplying this side by x, multiplying this side by x. So we get that dx is equal to x times du. I'm not going to write my bounds because we're changing things. And we talked about the last class period that there was 2 different ways to do this with our bounds of a definite integral with u substitution. So let's first rewrite this. So we have 3 all over x. So this parentheses, that's what we chose u to be. So we're going to replace that with u. And dx we found to be x times du. And so notice that that variable x that was in our integrand is now going to go away with what we substitute dx with, because we have an x there in the numerator now and an x in the denominator. So we've gotten this to the point that we know how to take the antiderivative. So this is where you're going to either change your bounds now, or if you don't change your bounds now, then at the end, after we take the antiderivative, we have to go back in, substitute in what u was in terms of x, and then we can evaluate it. I think it's easier if we change our bounds now. And actually, now I'm looking at it, we need to plug in 1. Maybe it's not so easy, but well, let's just do it. So here we have 2 different values for x. So when x is 1, we want to find u. So we have u is equal to 1 plus the natural log of 1. So remember, the natural log of 1 is 0. You're thinking to yourself, the natural log of 1 is log base e of 1. Logs are, what is that exponent you raise your base to? So what do we raise e to get back 1? Well, e raised to the 0 is 1. So this is 0. So u is equal to 1 plus 0, or u is going to equal, when x is 1, u is going to equal also 1. Now we have to look at when x is 2. Okay, so when x equals 2, we want to find u. Substitute it back in here. We get that u is equal to 1 plus the natural log of 2. The problem with this is that I don't know what the natural log of 2 is. I know it's e raised to some power gives me back 2. But I don't know what that number is. It's not a integer or whole number. And so we're just going to leave it like that, even though it looks ugly as an expression. We have 1 plus natural log of 2. Okay, so now we are all set. We can take the antiderivative of 3 over u. We can think of it with the properties of integration, that we can think of that 3 out front. And so really all we're looking at is the antiderivative of 1 over u. And that was that special case for the power rule that exponent couldn't be -1. If so, we think to ourselves, what do I take the I just said it. What do I take the derivative above to get 1 over u, which is the natural log of u. And because I already changed these in terms of u, I don't have to worry about going back and substituting this in. And so we're looking at this with the bounds from 1 to the natural log, 1 plus the natural log of 2. So first thing you're doing, you're plugging in your upper bound. So 3 natural log absolute value of 1 plus the natural log of 2. And then minus 3 natural log. And now we're plugging in 1 where we see our u. Well, again, the natural log of 1 is equal to 0. So this is 0 times 3. So this whole thing is going to be 0. So if they wanted us to just keep the exact answer, we can leave it as 3 natural log of 1 plus the natural log of 2. We really don't need those absolute values there because 1 plus the natural log of 2 is a positive number. If you plug this into the calculator, let's get the approximation. I have to put back on the video after I did my calculation. So putting that in the calculator, you get approximately 1.58. This is the exact form, 3 natural log of parentheses 1 plus natural log of 2. So for instance, if this was some sort of question on the exam and I didn't allow you to use a calculator, I would just tell you to keep it in the exact form. I don't expect you to know how to figure that out in your head. We're looking at another example of a definite integral. And in this example, again, we're going to have to use substitution. So when do I know I have to use substitution? I know, and what kinds of things do I look for to choose for that u to be? If you have a radical, like we do in this example, we have the integral from 0 to 8 of x to the 1/3 power, and then that's all times the square root, and underneath the radical, the radicand is x raised to the 4/3 power plus 9. So I don't know how to take the square or the antiderivative of a radical. I normally rewrote that as an exponent. The problem is rewriting that as an exponent, I still have a problem because there's more than one term underneath that radical. So if that's the case, then that's usually what you're going to choose u to be. Other things to look out for to choose u to be, if you have something raised to some high power in here, then choose what's inside the parentheses to be your u value. Or if you had 1 over more than one term in here, plus or minus, it doesn't matter what it is. And then a lot of times letting it be what the denominator is helpful. If you have e raised to something, like maybe x squared, then choose your u, because we don't know how to take we know how to take the derivative of that, but we don't know how to take the antiderivative of that. So choose your u to be the exponent. And the other one to look out for was that natural log. We don't know how to take the antiderivative of a log function. And so choose that to be your u value. And so those are kind of tricks of what to look for to figure out what to choose your substitution to be. So I see here, I can choose u to be what's underneath the radical. I also see that when I do that, there's still a value of x left in that integrand. And my hope, and I usually look at that when I'm choosing that u value, my hope is when I take the derivative of what I chose u to be, it will cancel out with whatever is left in there that has an x. And so we have u is equal to x to the 4/3 plus 9. So let's rewrite this or take the derivative of both sides. So we have derivative of a u is du equals the derivative of x to the 4/3. So bringing down our power down front, 4/3 x, subtract 1 from our power. So 4/3 minus 3/3 is 1/3. And derivative of a 9 is 0. And then we put on dx. So I'm going to divide both sides by 4/3, or I can think of it as multiplying both sides by 3/4. I don't like to really divide things by fractions. So if we multiply both sides by 3/4, that's going to clear this fraction here. And we're going to divide by this x to the 1/3. So we can think of this as multiplying both sides by 3 all over 4 x to the 1/3. So we get that our dx, because that's going to cancel, just leaving you with dx, is equal to 3/4, and then 4 is times x to the 1/3. Which I see, I have x to the 1/3 in my numerator here, so things are going to cancel out like I wanted them to. So we have the integral from 0 to 8, x to the 1/3, square root, this was our u value, and dx, oops, I forgot to tack on my du is equal to 3/4 x to the 1/3 power du. So I notice our x to the 1/3 cancel. And if they didn't cancel, then I either chose what u was wrong, or there's a way to go back in and manipulate x in terms of u. But things canceled out, so that's nice. I know I can pull that 3/4 if you want to, outside of the integral. So the integral, okay, this is again where I need to change my bounds. And I should have put in here that says x equals 8 because I changed it to u, or this, yeah, I put substitution. So let's go back there and figure out what that is. So we said u was x to the 4/3 plus 9. Or I can rewrite that as a radical, right? That 4/3 power is the same thing as the cubed root of x raised to the 4th plus 9. So when x is equal to 8, if we go in there, we can find u. So we have u is equal to the cubed root of 8. Then we're going to raise that to the 4th power plus 9. So the cubed root of 8 is 2. If I take 2 raised to the 4th power, I have 2, 4, 8, 16. So I'm left with 16 plus 9 here. So u is 25. So for this value, x equals 8, u is equal to 25. So we want to do the same thing with our bottom bound when x is 0. So if we go in there and we plug in 0, we get that u is equal to the cubed root of 0 raised to the 4th plus 9. So we get u is equal to 9. And instead of writing this, the square root of u, we're going to rewrite that as a power. So u to the 1/2 power d. Okay, so it's all set up that we can take the antiderivative and then we can evaluate it at our bounds. So adding 1 to our exponent. So 1/2 plus 2/2 is 3/2. Bring down my 3/4. And I'm evaluating this again from 9 to 25. Okay, so plugging it in, and at the same time, I'm going to rewrite it as a radical. So I'm plugging in 25 for u, and the 2 is in the denominator, so it's the square root of 25. And then I'm going to cube that number. Minus, so same thing, square root of 9 cubed. So the number that we take the square root of 25, the number we square to get 25 is 5. And 5 cubed, 5 times 5 times 5 is 125. Minus the square root of 9 is 3, and 3 cubed, 3 times 3 times 3 is 27. I'm running out of room. So let's now take 125 minus 27. So that's going to give me 98. So 3/4 times 98. Does 4 go in there evenly? No, it doesn't look like it does. I know that they both have a 2 in common at least. 2 goes into 4 twice, and 2 goes into 98 49 times. So 3 times 49. So I'm going to do 27. 3 times 9 is 27, carry my 2. 3 times 4 is 12 plus 2. So that's 147 all over 2. Or if we want to write it as a mixed number, that's 73 1/2. So I'll stop the video and restart a new video, but we'll look at now having some area under the curve and how to find that area. We did an example like that yesterday, but we'll look at some more examples. Not yesterday, Tuesday, but we'll look at some more examples now. So hopefully you noticed this while you were watching the video. Or watching me do this, that I forgot to, when I took my antiderivative, divide by my new power of 3/2, which is the same thing as multiplying by that reciprocal. So right there, I should have divided by 3/2 or multiplied by 2/3. So this should have been multiplied by 2/3. Multiplied by 2/3. But notice that 2/3, we can simplify that, right? The 3's cancel. This is 2 and 4. So that's just really left with 1/2. So this is 1/2 times this answer, which is going to change things from this point. So we have 1/2 all time 98, which equals 49.